Beneath our feet lies a world we rarely think about, a vast, shifting, molten realm that shapes continents, seeds the oceans, and breathes heat into the very crust we walk upon. Volcanoes, often imagined only as destructive forces, are in truth the great storytellers of Earth's inner life. Their eruptions, silent dormancy, and slow geological rhythms form a language the planet has spoken for billions of years. In this calm journey through Earth's fiery heartbeat, we will walk gently into the secret lives of volcanoes, their hidden chambers, their deep origins, and the astonishing ways they shape not only landscapes, but life itself. Each section will reveal something new and entirely different, weaving together planetology, deep time, chemistry, biology, and ancient Earth history. So take a deep breath, and let's begin our descent into the quiet, immense world beneath the crust. Section 1. The planet's molten foundation, where volcanoes are born. When we look at a volcano, a cone of rock, a plume of smoke, or a glowing river of lava, we are witnessing only the final exhale of a process that began unimaginably deep within the Earth. To understand the true nature of volcanoes, we must first travel downward, past the solid crust, and into the mysterious, shifting mantle where heat and pressure combine to create the molten foundation of our world. The mantle is not a vast ocean of liquid rock, as early scientists imagined, but a solid that behaves like a fluid over long periods of time. It is hot enough for minerals to soften and deform, flowing slowly like warm wax under the steady push of heat from the core. This heat is ancient, some of it left over from the planet's formation, some generated by the slow decay of radioactive elements like uranium and thorium. Together, these forces keep the deep Earth gently churning. This churning drives mantle convection, one of the most important processes on our planet. Picture massive currents of rock moving upward in broad, slow spirals. As warm mantle rises, it gradually cools, then sinks again, a cycle that takes millions of years. These convection currents drag continents, open oceans, raise mountains, and eventually create volcanoes. But magma does not form simply because the Earth is hot. In most cases, it forms because pressure changes. Deep beneath the crust, rocks may be hot enough to melt, but remain solid because they are under tremendous pressure. The same way ice can remain frozen under pressure, even at temperatures above its melting point. When rising mantle encounters a region of lower pressure, the rocks begin to melt. This is called decompression melting, and it is one of the primary ways magma is born. This process is responsible for volcanoes found along mid-ocean ridges, immense underwater mountain chains where tectonic plates slowly pull apart. As the plates separate, mantle rises to fill the gap, melts, and forms new crust in a continuous cycle of destruction and renewal. These underwater volcanoes, though rarely seen, create more volcanic rock than all surface volcanoes combined. Another way magma forms is through hydration melting, which occurs at subduction zones. When one tectonic plate dives beneath another, water trapped in minerals is released into the overlying mantle. Water, surprisingly, lowers the melting point of rock dramatically. With the addition of water, solid mantle begins to liquefy, forming magma that rises and eventually feeds some of the most explosive volcanoes on Earth. These volcanoes, such as those around the Pacific Ring of Fire, owe their power to the unique chemistry of subducted crust. There is also a third, more mysterious birthplace of magma, mantle plumes or hot spots. These are believed to be narrow columns of unusually hot mantle, rising all the way from the boundary between the core and the mantle, almost 3,000 kilometers deep. When these plumes reach the surface, they create volcanoes in the middle of tectonic plates, such as those of Hawaii and Iceland. Mantle plumes are one of the planet's great geological mysteries, long-lived, focused, and capable of creating chains of volcanoes stretching across oceans as tectonic plates move over them. But the story of magma does not end with its formation. Once created, molten rock collects in chambers within the crust, dynamic reservoirs that can grow, shrink, and evolve chemically over thousands to millions of years. These magma chambers are rarely uniform. They are layered, complex, and constantly changing. Crystals grow within them, gases accumulate, and different layers of magma interact in fluid, unpredictable ways. Some magma chambers are relatively stable and quiet, slowly cooling without ever causing an eruption. Others build pressure over centuries, storing gases and heat until the system reaches a tipping point. When the pressure becomes too great, magma breaks through the crust, seeking the fastest path upward, sometimes forming gentle lava flows, other times exploding violently and reshaping entire landscapes. Despite their dramatic potential, volcanoes are fundamentally a sign of a living planet. Without internal heat, Earth would be geologically dead, its surface unchanged for billions of years, like the Moon or Mars. Volcanoes remind us that our planet is active, evolving, and creative. They build new land, cycle nutrients, release gases that shape the atmosphere, and stir the deep Earth's energy into the surface world. The molten foundation that gives birth to volcanoes is therefore not a threat, but a heartbeat, the slow, fiery pulse of a planet that is still alive. Section 2. The hidden architecture of magma chambers. Most people imagine a magma chamber as a giant underground pool, a vast cavern filled with glowing liquid rock, waiting beneath a volcano like an enormous pot of lava. But the real structure of a magma chamber is far more intricate, far more dynamic, and far more surprising. In many ways, a magma chamber is less like a lake and more like a living organ within the Earth's crust. It grows, contracts, circulates, evolves, and transforms itself continuously, shaped by the delicate balance between heat, pressure, and chemistry deep below the surface. To understand the hidden architecture of magma chambers, we first need to understand that they are not empty spaces. Contrary to the popular image, subterranean caverns filled wall-to-wall with magma almost never exist. Instead, a typical magma chamber is more like a region of partially melted rock, where solid crystals float in a thick, molten mixture. This mixture is not uniform. It has layers of different temperatures, densities, crystal percentages, and chemical compositions. Some regions may be nearly fully molten. Others may contain more solid material than liquid. Think of it as a vast, slow-moving stew, where each ingredient responds to heat and pressure in its own way. At the top of the chamber, gases accumulate: carbon dioxide, sulfur dioxide, water vapor, and other volatile molecules. These gases are the secret architects of volcanic behavior. As pressure builds, gases try to escape, forcing cracks in the surrounding rock, like steam pressing against the lid of a sealed pot. If the gases remain trapped, pressure continues to rise silently. If they escape slowly, the system remains stable and calm. The central regions of a magma chamber often experience internal convection, driven by temperature differences. Hotter magma rises, cooler magma sinks, and the entire system can circulate for thousands of years. This circulation affects everything: the minerals that crystallize, the viscosity of the melt, and the likelihood of eruption. Crystallization is one of the most important processes in shaping the chamber's architecture. As magma cools, minerals begin to form in a predictable sequence. Heavy crystals sink toward the bottom, creating a layer of slowly accumulating solid rock called a cumulate. Lighter crystals may remain suspended or float. As minerals crystallize, the leftover melt becomes enriched in elements not easily captured by early forming crystals. This process, known as magmatic differentiation, can transform a uniform mass of molten rock into a mosaic of chemically distinct layers. This is why a single volcanic system can produce wildly different types of lava over time: basalt in one eruption, andesite in another, rhyolite in yet another. The magma is not a fixed substance. It evolves. But magma chambers are not closed worlds. They are constantly fed by new magma rising from the mantle. When fresh magma enters a chamber, it can dramatically reshape its architecture. Hot magma injected into cooler, more stagnant regions can stir the system, remelt crystals, mix chemical layers, or destabilize gas pockets. These injections often act like the sudden addition of heat beneath a pot, reawakening convection, altering pressure, and pushing the system closer to eruption. Sometimes, instead of mixing smoothly, different magmas remain separate within the same chamber, forming distinct pockets or layers. Such coexistence is similar to oil and water in a glass. Immiscible magmas with different temperatures or chemical compositions can coexist without blending. When eruptions draw material from multiple pockets simultaneously, the resulting lava is a complex hybrid, revealing the chamber's diverse architecture. Another essential feature of many magma chambers is the presence of sills and dikes, long, sheet-like intrusions where magma has forced its way horizontally or vertically through cracks in the surrounding rock. These intrusions act as both highways and escape routes. Some feed volcanic vents, others spread sideways, cooling underground to form layers of igneous rock that may eventually become visible on the surface after millions of years of erosion. In some volcanic systems, a single magma chamber may be connected to deeper reservoirs, forming a multi-tiered structure like a branching network. These layered systems can contain mantle-derived magma in deeper chambers and more evolved magma in shallower ones. Over geological timescales, this tiered architecture can rearrange itself, merging, dividing, or collapsing, depending on pressure, temperature, and the influx of new molten material. Despite their apparent scale, magma chambers are delicate systems. The roof of a magma chamber, the rock layer above it, is often under immense stress. If too much magma accumulates, or if heat weakens the rock, the roof may begin to bulge upward, forming surface features like ground inflation. Scientists can detect these changes with GPS and satellite radar, watching as the Earth rises or falls by centimeters or even meters. Sometimes the most profound changes occur without any eruption at all. A chamber may grow steadily for centuries, storing heat and pressure, only to cool and solidify again. This quiet solidification can trap gases in crystal lattices, freeze chemical gradients in place, and preserve a snapshot of the chamber's internal organization. Millions of years later, tectonic uplift or erosion may expose these once hidden chambers as beautiful igneous formations, layered cliffs, crystal-rich rocks, and complex textures that reveal the deep, molten creativity of the Earth. But not all magma chambers remain intact forever. In extremely large volcanic systems, the withdrawal of magma during a major eruption can weaken the chamber's roof so much that it collapses inward. This collapse forms a caldera, a vast depression in the landscape that may stretch for tens of kilometers. Calderas are among the planet's most dramatic geological features, created not by explosion, but by the slow, catastrophic sinking of the surface into the emptied chamber below. Yet even then, the magma chamber rarely disappears entirely. It often begins refilling immediately, rebuilding its architecture in preparation for another cycle. In all of these ways, layering, convection, crystallization, replenishment, intrusion, collapse, magma chambers write their own internal story. They are neither static nor simple. They are dynamic, evolving, deeply chemical environments where heat and pressure sculpt molten rock into an ever-changing architecture. They are the secret engines of volcanic life, pulsing slowly in the dark beneath mountains and deserts and oceans. And perhaps the most extraordinary truth is this: a magma chamber is not something separate from the volcano. It is the volcano, its mind, its heart, and its memory. Section 3. The Many Personalities of Volcanoes. Why no two are alike. Volcanoes are often spoken of as if they were uniform, mountains with vents, magma, and eruptions. But in truth, each volcano is a distinct personality shaped by millions of years of geological history. They differ in their chemistry, in their temperament, in their behavior, and even in the landscapes they create. Some whisper, some roar, some grow patiently for ages, some erupt explosively with little warning, some ooze gentle flows of molten rock, while others send ash high into the stratosphere like a volcanic exhale reaching toward the edge of space. This extraordinary diversity begins with something deceptively simple: the composition of the magma. Melted rock is not a single substance. It contains varying proportions of silica, gases, metals, and minerals. Silica, in particular, is the ingredient that most determines a volcano's personality. High silica magma tends to be thick, resistant to flow, and prone to trapping gases. Low silica magma, by contrast, is fluid and easy-flowing. This seemingly small difference shapes everything from eruption style to volcano shape. Volcanoes fed by low silica basaltic magma tend to be broad and gently sloping. These are the shield volcanoes, named for their resemblance to a warrior's shield laid flat on the ground. Mauna Loa and Kilauea in Hawaii are perhaps the most famous examples. Their lava pours out in wide, fluid rivers that can travel kilometers before cooling. Eruptions here are usually calm and steady, fountains of orange lava dancing upward in arcs, accompanied by soft rumbles that sound more like the earth sighing than breaking. On the opposite end of the spectrum lie stratovolcanoes, tall, steep, and dramatic. These volcanoes, such as Mount Fuji, Mount St. Helens, and Vesuvius, are fed by more silica-rich magmas. Their lavas are thicker and more reluctant to flow, often clogging vents and allowing enormous pressure to build. When the pressure becomes too great, gases trapped inside the sticky magma escape violently, fragmenting the melt and blasting it outward as ash, pumice, and volcanic bombs. These eruptions can reshape entire landscapes within minutes, carving new valleys, flattening forests, and altering climates. But even these two broad categories fail to capture the true diversity of volcanic personalities. Between basaltic shields and explosive stratovolcanoes lies a spectrum of intermediate forms. Cinder cones, for instance, are small, steep hills built from fragments of cooled lava that fall around a vent, like confetti settling after an event. They can form rapidly, sometimes growing hundreds of meters tall in mere weeks. Lava domes, by contrast, grow slowly and quietly, formed from extremely viscous magma that piles up over a vent like bread dough rising. These domes may look calm, but their interiors can be volatile. Pressure can build beneath them until the dome cracks or collapses, unleashing pyroclastic flows, searing avalanches of gas and ash that sweep downslope at hurricane speeds. Then there are caldera systems, some of the most complex volcanic structures on Earth. These are not single mountains, but wide depressions formed when enormous magma chambers empty and the surface collapses into the void. The Yellowstone caldera, for example, is so large that one can stand inside it without recognizing its boundaries. Such systems often host multiple types of volcanic activity simultaneously: geysers, steam vents, hot springs, lava flows, and explosive eruptions, all fed by a deep, dynamic network of magma reservoirs. One of the lesser-known personalities in the volcanic world is the fissure eruption, in which magma emerges from long cracks rather than a central vent. These eruptions can produce curtains of fire, stretching across the landscape. Glowing lines of fountains, as if the ground itself has torn open to reveal a fiery pulse. Iceland's Loki eruption and the recent Fagradalsfjall events are iconic examples of this dramatic style. Volcanoes also differ in their behavior over time. Some are persistently active, releasing small amounts of magma regularly and maintaining a relatively stable internal system. Others are episodic, quiet for centuries before awakening suddenly with immense force. Still others may erupt once in a geologic instant, then rest for hundreds of thousands of years. Even volcanoes with similar shapes can behave differently depending on the gas content of their magma. Gas-rich systems tend to be more eruptive, their internal chemistry resembling a shaken bottle of carbonated water. Gas-poor systems, by contrast, may release lava gently without much explosive activity. The balance between gases, pressure, and magma viscosity is one of the primary reasons no two volcanoes ever behave the same way. The tectonic setting also influences a volcano's personality. Volcanoes at subduction zones have access to water-rich, chemically diverse magmas, making them prone to powerful explosions. Volcanoes at mid-ocean ridges tend to produce steady basaltic flows. Hotspot volcanoes, such as those in Hawaii or beneath the Canary Islands, are shaped by deep mantle plumes that rise independently of the surrounding plates. Even the surrounding environment, ice, water, or the atmosphere, can dramatically change a volcano's behavior. Subglacial eruptions, like those in Iceland, involve magma interacting with ice, producing vast floods, ash clouds, and unusual formations of glassy volcanic rock. Underwater volcanoes behave differently still, their eruptions muffled by ocean pressure, creating pillow lavas that look like molten balloons frozen in time. With such variability, scientists often describe volcanoes as having personalities, and it's more than just poetic language. Volcanoes remember their past. Their behavior is shaped by centuries of accumulated history, the architecture of their magma chambers, the composition of stored magma, the strength of old conduits, and the existence of hidden pockets of melt left over from previous eruptions. A volcano that once erupted explosively may erupt gently centuries later, or the reverse. Its temperament is never fixed. Ultimately, each volcano is the product of countless invisible forces: mantle chemistry, tectonics, pressure, temperature, gas content, crustal structure, and time. This is why scientists can recognize patterns but never predict behavior with perfect accuracy. Volcanoes are not machines. They are living geological systems. Their differences remind us that the Earth itself is not a static world, but a vibrant, evolving planet filled with complexity beneath the surface. And in this complexity lies beauty, a constantly shifting mosaic of heat, rock, gas, and deep time, shaping the landscapes we walk upon and the air we breathe. Section 4. Volcanoes that build worlds: how eruptions create continents, islands, and atmospheres. To most people, a volcano is a symbol of destruction. Ash clouds darkening the sky, lava consuming forests, and explosions reshaping whole regions. But in geologic truth, volcanoes are far more than engines of ruin. They are architects. They are creators. They are the quiet craftsmen of the continents, the sculptors of the seafloor, and the ancient chemists that once shaped Earth's atmosphere. Without volcanoes, the world as we know it simply would not exist. Land would be scarce, oceans would be different, and life, if it existed at all, would have unfolded in a drastically altered landscape. To understand how volcanoes build worlds, we must begin at the deepest levels of planetary history. In the infancy of Earth, more than 4 billion years ago, the planet's surface was still forming from impacts, collisions, and molten debris. Volcanoes were everywhere, not the isolated peaks we see today, but an entire surface mottled with vents, fissures, and plumes of incandescent rock. These eruptions gradually cooled and thickened the crust, creating the first fragments of continental material. But not all volcanic rock is the same. Basalt, which forms the ocean floors, is dense and dark. Granite-like rocks, which form the core of continents, are lighter and more buoyant. This fundamental difference explains why continents float high on the mantle, while oceanic crust spreads out like a heavy, cooled skin. Over billions of years, volcanoes produced enough varied magma to build these contrasting types of crust, the scaffolding upon which continents slowly assembled. In addition to constructing land, volcanoes also play a central role in creating islands, some of the most striking geological features on Earth. Islands born of volcanic activity arise in three main ways. The first are hotspot islands, created when plumes of hot mantle material rise from the deep earth and melt through the crust. Hawaii is perhaps the most iconic example. As the Pacific Plate moves over the stationary hotspot, new volcanoes form one after another. This process creates long chains of islands, each one a time capsule of volcanic history, moving farther from the hotspot as the plate drifts. Over millions of years, these islands erode, sink, and eventually disappear beneath the waves, replaced by newly formed peaks at the front of the chain. The second type are island arcs, formed at subduction zones, where one tectonic plate plunges beneath another. As the descending plate releases water into the mantle, magma forms and rises through the crust, building arcs of volcanoes like the Aleutian Islands, Japan, and the Philippines. These arcs are dynamic, growing more complex over time as eruptions stack layer upon layer of rock, gradually building entire nations upon the foundations of molten earth. The third are rift-related volcanic islands, which form when tectonic plates pull apart and magma fills the widening gap. Iceland, perched atop the mid-Atlantic ridge, is a dramatic example. It is a place where new crust is born directly above sea level, a reminder that the Earth is still actively writing new land into existence. But volcanoes do more than shape geography. They also shape atmospheres. This is true not only on Earth, but on other worlds in our solar system. On early Earth, volcanic gases, water vapor, carbon dioxide, nitrogen, sulfur compounds were essential ingredients in forming the primordial atmosphere. Without volcanic outgassing, there would have been no air to breathe, no oceans to cradle life, and no climate to regulate the planet's temperature. Water vapor, released from billions of years of volcanic eruptions, contributed to the formation of Earth's oceans. As the planet cooled, this vapor condensed and fell as rain, filling the basins carved by tectonic and volcanic processes. The oceans that now dominate Earth's surface were built, in a significant sense, by volcanoes. Volcanoes also played a role in balancing the planet's early greenhouse effect. While eruptions emit carbon dioxide, they also release materials that aid in long-term carbon removal. For instance, fresh volcanic rock weathers quickly, drawing CO2 from the atmosphere as it breaks down. This natural cycle helped stabilize Earth's climate, preventing runaway heating or freezing, and maintaining conditions suitable for life. On other planets and moons, volcanoes have performed similar world-shaping roles. Venus, for example, is covered in volcanic plains and giant shield volcanoes. Io, a moon of Jupiter, hosts the most volcanically active surface in the solar system, constantly reshaped by eruptions driven by tidal heating. Mars features Olympus Mons, the largest volcano ever discovered, 3 times taller than Everest, so large it defies human comprehension. These extraterrestrial volcanoes demonstrate that volcanic creation is a universal process, one linked to planetary energy, gravity, and composition. Returning to Earth, we also find that volcanic eruptions can create completely new ecosystems, sometimes in places that previously had none. When a new island forms, such as Surtsey off the coast of Iceland in the 1960s, it emerges from the sea, sterile and lifeless. Over time, however, life begins to arrive. Birds, insects, plants carried by wind or waves. Over the decades, a thriving ecosystem develops on land that was once a glowing mound of lava. These natural laboratories allow scientists to watch ecological succession from its very first chapters. Volcanoes also enrich soils with minerals. Regions like the highlands of Java or the slopes of Mount Vesuvius possess famously fertile land because volcanic ash contains nutrients that enhance plant growth. Civilizations have risen around volcanoes for precisely this reason, though sometimes they have paid the price when those same volcanoes awaken again. And there is another, more subtle way in which volcanoes build worlds: through renewal. Though volcanic eruptions can devastate landscapes, they also renew them. Forests regrow in ash-covered valleys. Rivers carve new channels through hardened lava. Life adapts, evolves, and reclaims the land. Over long timescales, volcanoes act not only as forces of change, but as catalysts for diversity. In the deepest sense, volcanoes are not separate from the world. They make the world. Continents grow, islands rise, atmospheres evolve, life expands and adapts, all of it tied to the slow, ancient pulse beneath our feet. The next time you see a volcano, in a photo, on a map, or on the horizon, remember that you are looking at more than a mountain. You are looking at the force that gave Earth its shape, its oceans, its air, and its story. Section 5. When volcanoes sleep. Dormancy, silence, and the illusion of safety. There is a special kind of stillness in the presence of a dormant volcano. It is not like the quiet of an empty room or a calm lake. It is a deeper quiet, a geological pause, a moment suspended between breaths. To the untrained eye, a dormant volcano looks peaceful, even harmless. Its slopes are softened by forests, its craters filled with lakes, and its flanks inhabited by towns and farms. But this tranquility can be misleading, because the word dormant does not mean dead. It means asleep. And sleep, as we know from Earth's long memory, is never guaranteed to last. Dormancy is one of the most misunderstood states in volcanic science. People often imagine volcanoes as either erupting or extinct. But most volcanoes exist in the wide spectrum between those two extremes, resting, recharging, waiting for the next movement of molten rock deep below. This waiting period can last decades, centuries, even tens of thousands of years. And during that time, the volcano's outward face grows quiet, but the slow, unseen processes within it continue operating, shaping the future in ways invisible from the surface. To understand dormancy, we must first understand what causes a volcano to fall silent. After an eruption, the magma chamber, the reservoir that feeds the volcano, may drain or cool. Pressure drops, gas escapes, and the pathways through which magma once surged seal themselves with new minerals. The volcano becomes structurally calmer, less primed for immediate activity. But this calmness does not mean the end. Deep beneath the crust, mantle plumes and tectonic interactions continue generating magma. Over time, new molten rock may flow into the chamber, reheating it, pressurizing it, and preparing it for another awakening. Some volcanoes cycle through dormancy with astonishing regularity. Others are unpredictable, going quiet for generations before returning with sudden violence. Consider Mount Vesuvius in Italy. Before its catastrophic eruption in 79 CE, which buried Pompeii and Herculaneum, it had been quiet for centuries. The people living on its fertile slopes believed the mountain was benign. They farmed its soil, built villas on its ridges, and treated it as a source of life, not danger. Yet beneath their homes, magma had been accumulating silently, compressing gases and building pressure until the mountain finally opened again. The deceptive peace of dormant volcanoes has shaped human history. Many great cities, Naples, Arequipa, Quito, Kagoshima, sit on the shoulders of sleeping giants. Their presence is not irrational. Volcanic regions are fertile, rich in minerals, and often situated along coastlines or river systems that make them ideal for settlement. A dormant volcano can quietly nurture life for centuries. But the trade-off is always there. The recognition that one day, perhaps long after memory fades, the volcano may wake. Adding to this uncertainty is the challenge of predicting volcanic reactivation. Scientists monitor dormant volcanoes using a combination of techniques: seismic sensors to detect small earthquakes, gas readers to measure the chemistry of escaping fumes, satellite imagery to track land deformation, and thermal cameras to identify heating patterns. These technologies allow researchers to observe a volcano's internal behavior even when it is outwardly calm. When magma rises, it rarely does so silently. It fractures rock, heats groundwater, releases gases, and subtly pushes the ground upward, all signs that specialists can detect. But predicting when a volcano will erupt remains a complex task. Some volcanoes stir for decades without erupting. Others awaken in a single season. The Earth's crust is not a simple machine. It is a dynamic, living structure. And each volcano has its own personality, shaped by its magma composition, its conduit system, its tectonic setting, and its long geological history. A powerful example of sudden awakening is Mount Pinatubo in the Philippines. Before 1991, it was considered dormant, a quiet, forest-covered peak that seemed harmless enough. Few people living nearby even knew it was a volcano. Then, with surprising speed, it came back to life. Steam explosions, ground cracks, and sulfur emissions signaled its reawakening. Within weeks, the mountain erupted violently, producing one of the largest eruptions of the 20th century. Dormancy, as that event reminded the world, is not the same as safety. But the story of sleeping volcanoes is not just one of risk. It is also one of deep geological patience. A dormant volcano can act as a natural archive, preserving records of past eruptions in layers of ash, rocks, and minerals. By studying these layers, geologists can reconstruct a volcano's history and better understand its future. The thickness of old ash deposits reveals the power of past explosions. The chemistry of minerals offers clues about the magma deep below. Even ancient lava flows act as pages in a geological book, each telling a story about how the volcano behaved long before humans kept written records. This slow, methodical science helps transform fear into understanding. A dormant volcano becomes not just a threat, but a teacher, a guide to the long rhythms of the earth. The silence between eruptions is not empty. It is full of information waiting to be uncovered. Dormancy can also create unique environments. Craters may fill with water, forming lakes of remarkable beauty. Lava tubes become habitats for rare creatures. Ash fields evolve into meadows or forests. Over time, life adapts to the dormant volcano, and the volcano, in turn, becomes part of the local ecosystem. Some dormant calderas even form entire landscapes within their boundaries. Fertile basins where communities flourish, unaware that they live inside the footprint of an ancient eruption. Yet despite all this calm, the volcano beneath remains a reservoir of power. The stillness is temporary, a pause in a cycle that spans far longer than human lifetimes. Dormant volcanoes remind us of the humility required when studying natural systems. Earth does not operate according to human schedules. A volcano that has been silent for 1,000 years may simply be gathering its breath. In the end, the illusion of safety is not a flaw of the volcano. It is a misunderstanding of the timescale on which volcanoes live. Their silence can last longer than entire civilizations, longer than languages or empires or traditions. But on geological time, these quiet periods are merely intervals. The Earth moves slowly, but it always moves. When standing before a dormant volcano, it is tempting to think of it as static. But the truth is gentler and more profound. It is resting, not finished. Beneath its calm surface lies the same fiery heartbeat that once built continents and islands. Its silence is part of the rhythm of the planet, a deep inhale, preparing one day for another exhale of molten breath. Section 6. The hidden chemistry of magma, colors, crystals, and the artistry of melted earth. Before magma bursts into the open world as glowing lava, it exists in a secret universe deep beneath our feet, a universe of chemistry, pressure, and heat. Most people imagine magma as a simple, fiery liquid, swirling like molten metal, but magma is far more complex. It is a living mixture of minerals, crystals, dissolved gases, and chemical reactions that shift with every rise and fall inside Earth's crust. It is, in many ways, Earth's most ancient painter, crafting the colors and textures of new rocks, shaping landscapes, and recording the planet's internal processes in every solidified layer. To understand a volcano, one must understand the chemistry of magma, because this chemistry determines everything from the color of lava to the violence of eruptions. Some magma flows gently, spreading in wide, soft rivers. Other magma explodes with violent force, tearing apart mountains and sending ash into the stratosphere. The reason lies in molecular structures, gas content, and the crystallization processes that unfold in the deep, dark spaces where no light reaches. At its core, magma is molten rock composed of three main components: liquid melt, solid crystals, and gases. The melt is the fluid part, an intricate blend of silica, metals, and oxides. The crystals are tiny mineral fragments suspended in the melt, and they form as the magma begins to cool. The gases include water vapor, carbon dioxide, sulfur dioxide, and dozens of trace elements that dramatically influence eruptive behavior. Silica, the chemical backbone of most Earth materials, plays the starring role. High silica magmas are thick, sticky, and resistant to flow. They trap gases, forcing pressure to build. This type of magma creates explosive eruptions like those of Mount St. Helens or Krakatoa. Low silica magmas, on the other hand, are thin and runny. They allow gases to escape smoothly, producing gentle, steady flows like those seen in Hawaii. This single chemical difference, the concentration of silicon and oxygen molecules, determines whether a volcano whispers or roars. Yet magma's chemistry goes far beyond silica alone. Inside the melt, a symphony of minerals interacts. Iron and magnesium create dark basaltic lavas. Potassium and sodium contribute to lighter, rhyolitic flows. Calcium and aluminum influence the formation of plagioclase crystals, which often appear as shimmering white specks embedded in frozen lava. Every mineral present reflects specific temperatures, pressures, and chemical histories. Like ingredients in a recipe, they reveal what paths the magma traveled on its way to the surface. As magma rises, temperature and pressure begin to change, and crystals start to form. Crystallization is not merely cooling. It is a kind of geological choreography. Different minerals crystallize at different temperatures, each forming its own shapes and patterns. Olivine, for example, is one of the first minerals to crystallize from hot magma. It forms beautiful green crystals, giving certain volcanic rocks their subtle olive tint. Pyroxene follows next, forming dark, glossy structures. Later, as the magma cools further, feldspar and quartz begin to appear. The crystallization sequence tells scientists the exact temperature at which various minerals formed, allowing geologists to reconstruct the thermal history of a volcano. A sample of volcanic rock is like a time capsule, a record of changing conditions inside the Earth. Under a microscope, each crystal's shape, size, and chemical zoning becomes a clue, revealing how fast the magma cooled. Whether it paused in underground chambers or whether multiple magma batches interacted, these interactions, known as magma mixing, produce some of the most stunning volcanic features on Earth. Imagine two magmas, one hot, dark, and fluid, the other cooler, pale, and viscous, colliding beneath the surface. Instead of blending smoothly, they swirl around each other, weaving patterns like marbled stone. When these mixtures erupt, they create rocks with intricate streaks, spirals, and patches of contrasting colors. The beauty of these patterns rivals any crafted artwork, yet they form naturally, sculpted by pressure, motion, and time. Volcanic gases also shape the chemistry of eruptions. Water vapor is the most influential, comprising up to 97% of volcanic gas emissions. When water dissolves in magma under high pressure, it remains invisible. But as the magma approaches the surface and pressure decreases, the water bubbles out, just like carbon dioxide escaping a soda bottle when opened. This degassing process can drive explosive eruptions if the bubbles remain trapped, or gentle lava flows if the gases escape easily. Sulfur is another critical element. It creates sulfur dioxide gas, which can react with the atmosphere to form delicate sulfate crystals that reflect sunlight. These crystals can cool global temperatures for months or years after major eruptions. Iron and titanium contribute to deep black volcanic glass, such as obsidian. Other trace elements produce brilliant colors. Cobalt makes blues. Copper produces greens. Manganese can add shades of purple. Volcanic landscapes are not simply barren. They are geological palettes. Inside lava's glow, chemistry continues to paint. As lava cools on the surface, gases escape, leaving behind bubbles that become vesicles, small, round holes in the rock. Pumice forms when gas-filled lava cools so quickly that it becomes full of these holes, turning the rock so light it can float on water. On the other end of the spectrum, obsidian forms when lava cools so rapidly that no crystals develop at all, creating glass with an almost ethereal shine. These contrasts, from airy stone to razor-sharp black glass, emerge from subtle changes in cooling rates and gas contents. Some of the most unusual volcanic rocks owe their existence to extreme chemistry. Pele's hair, for example, is made of thin strands of volcanic glass, stretched into golden fibers as lava droplets are pulled by wind. These strands can be so fine that they resemble human hair, and they shimmer in the sun like fragile threads of woven light. Pele's tears, as the small glass beads are called, form in a similar way. Droplets of lava cooled midair, solidifying into perfect tiny spheres. Underground, slow-cooling magma chambers form vast crystalline bodies known as plutons. These chambers may take thousands of years to cool, allowing minerals to grow into large, spectacular crystals. Granite, with its visible quartz, feldspar, and mica, is the end product of such chambers. Every crystal within it, whether milky white or smoky gray or reflective silver, tells a story of patient cooling and layered chemistry. Ultimately, magma's chemistry is a reminder of the Earth's artistic nature. Beneath the destructive eruptions and molten flows lies a delicate system governed by structure, temperature, molecular bonds, and the flow of energy. Every volcanic landscape, every basalt plain, every obsidian ridge, every pumice field is a gallery carved by heat and shaped by chemical evolution. In the world beneath our feet, Volcanoes express themselves not only through eruptions, but through the colors and crystals that fill the rocks they leave behind. It is Earth speaking in mineral languages, writing its history in luminous patterns and molten art. Section 7. Antarctica's Hidden Fire, Volcanoes Beneath the Ice. At first glance, Antarctica seems like the last place on Earth where one might expect to find fire. It is a continent sculpted by ice, wrapped in silence, and dominated by temperatures that can plunge below -80 degrees. But beneath its frozen surface lies a world that could not be more different. A realm of volcanic mountains, molten rock, geothermal energy, and hidden chambers of heat. In this unlikely landscape, ice and fire coexist, creating one of the most mysterious and least understood volcanic systems on the planet. Most people imagine Antarctica as a flat sheet of white, but its geography is far more complex. Beneath the ice, the continent is home to more than 140 identified volcanoes, making it one of the most volcanically rich regions on Earth. Some stand as towering peaks above the ice, like Mount Erebus, constantly breathing out plumes of steam, while others remain entirely buried, hidden under ice sheets that are kilometers thick. These concealed volcanoes have been discovered through remote sensing, ice-penetrating radar, and gravitational mapping, each method revealing pieces of a vast, fiery landscape that lies beneath kilometers of frozen silence. The most iconic of Antarctica's volcanoes is Mount Erebus, located on Ross Island. Unlike most volcanoes on Earth, Erebus contains one of the few persistent lava lakes in the world. Its molten surface glows like a fiery eye, constantly churning, bubbling, and sending up small eruptions. This lake has existed for decades, possibly centuries, creating an extremely rare window into Earth's mantle processes. Lava lakes are delicate systems that require stable conditions, a precisely balanced supply of magma rising from below. Too much magma, and the lake erupts violently. Too little, and the lake freezes over. Erebus has mastered this balance, allowing scientists to observe near-continuous volcanic activity in one of the coldest, most remote places on Earth. Yet Erebus is only one part of Antarctica's volcanic story. Across Marie Byrd Land in West Antarctica, buried volcanoes lie beneath vast ice sheets. Here, hot spots, plumes of molten rock rising from deep within the mantle, feed systems of warmth that slowly melt the ice from below. This geothermal heat influences how the ice flows, how it fractures, and even how rapidly it moves toward the ocean. In many ways, volcanoes beneath Antarctica act like secret engines, driving the behavior of the ice above them. One of the most fascinating features of this region is the West Antarctic Rift System, a massive tear in Earth's crust, stretching for hundreds of kilometers. Within this rift, dozens of volcanic structures rise from the bedrock. Some of them have erupted within the past 10,000 years, which, in geological terms, is incredibly recent. Others remain active, slowly heating the ice above them. Scientists believe that volcanic heat contributes to the presence of subglacial lakes, liquid bodies of water trapped beneath the ice, some of them larger than major cities. Lake Vostok, one of the largest and most ancient of these lakes, lies more than 4 kilometers beneath the surface and remains liquid due to geothermal warmth. This hidden interplay of heat and ice is one of Antarctica's most captivating mysteries. When a volcano erupts beneath an ice sheet, the eruption behaves very differently from one that occurs in open air. Instead of fire fountains and lava flows, the heat melts enormous chambers within the ice. These chambers fill with water, building pressure until they burst outward in what are known as Jokulhlaups, catastrophic glacial floods that can carve deep channels and transport massive blocks of ice and rock. These events are common in Iceland, but Antarctica's immense ice thickness means the processes are magnified on a continental scale. Even when eruptions do not occur, volcanic heat can weaken the ice sheet from below, creating unstable zones where ice can collapse or accelerate toward the ocean. Such hidden volcanic activity may help explain why certain parts of West Antarctica have thinned significantly in recent decades, not solely due to atmospheric warming, but due to heat rising from the Earth itself. One of the most surprising implications of Antarctic volcanoes is that they may have influenced global climate in the distant past. Massive eruptions beneath the ice could have released giant pulses of meltwater into the oceans, altering sea levels and ocean circulation. Some scientists believe that ancient volcanic events in Antarctica might have triggered periods of rapid glacial retreat, helping to end ice ages or reshape coastlines across the world. The idea of volcanoes erupting beneath so much ice may sound like a contradiction, but in reality, it is a delicate dance of extremes. The ice sheet acts as both a barrier and a partner. It suppresses explosions by exerting enormous pressure, forcing magma to move in unexpected ways. At the same time, it channels meltwater to specific pathways, sculpting subglacial valleys and networks. The ice in turn responds to the heat, cracking, melting, shifting, and occasionally surging with concealed energy. Perhaps the most astonishing revelation of all is that scientists have detected volcanic tremors occurring right now beneath the ice. One such discovery took place near Mount Sidley, a huge dormant volcano whose last eruption occurred millions of years ago. Beneath its snow-covered slopes, sensors picked up seismic signals consistent with magma movement. This does not mean an eruption is imminent, but it does mean that Antarctica is far from geologically silent. Its volcanic systems are alive, breathing slowly and quietly beneath the frozen surface. The presence of active volcanoes beneath the ice challenges our perceptions of Antarctica. Instead of a cold, dead continent, it becomes a place of hidden dynamism, where molten rock and freezing temperatures coexist in fragile equilibrium. It forces scientists to rethink how ice sheets evolve, how geothermal energy interacts with climate, and how much of Earth's volcanic activity remains unseen. Antarctica is a world of paradoxes, one where glaciers float above rivers of melt, where mountains lie buried under frozen oceans, and where the most inhospitable landscape on Earth hides glowing chambers of liquid fire. Its volcanoes remind us that even the coldest places hold warmth at their core, and that beneath the silent white surface lies one of the most fascinating geological stories on the planet. Section 8. Volcanoes that created life, How eruptions built our atmosphere and oceans. Long before forests grew, long before animals walked or oceans teemed with fish, Earth was a world of fire. In the planet's earliest ages, the surface was a molten ocean, constantly reshaped by relentless volcanic activity. It may feel strange to imagine that the violent eruptions we fear today are the very processes that once made our world habitable. But the truth is that volcanoes played a profound and nurturing role in creating life. They built the atmosphere, forged the oceans, shaped the continents, and supplied the chemicals that would eventually weave themselves into living cells. When Earth first formed 4.5 billion years ago, it was a hostile, barren sphere of rock. Its surface was constantly bombarded by meteorites and heated by internal chaos. There was no breathable air, no liquid water, and certainly no life. The only forces capable of transforming this raw, molten planet into a living world were those rising from within, volcanoes. The earliest volcanic eruptions released vast amounts of gases trapped inside the young planet. These gases created Earth's first atmosphere, an atmosphere that bore almost no resemblance to the one we breathe today. It was thick with carbon dioxide, nitrogen, methane, sulfur compounds, and water vapor. There was no oxygen, no ozone layer, and no protection from the sun's ultraviolet radiation. Yet this primordial atmosphere was the foundation upon which all life would later grow. Water vapor was the most important gas released by early volcanoes. As Earth cooled, this water vapor condensed into clouds, fell as rain, evaporated again, and fell once more. For millions of years, the young planet experienced relentless storms. Warm rains that slowly filled vast basins and depressions in the crust. These rains eventually became Earth's first oceans. Without volcanoes, there would have been no atmospheric moisture and therefore no oceans at all. Every drop of water on Earth today, from the deepest ocean trench to the moisture inside your own cells, is connected to these ancient volcanic breaths. As volcanic activity continued, more complex geological processes began to shape the planet's surface. Lava flows cooled into solid rock, forming the first islands and proto-continents. Plate tectonics, driven by the heat of Earth's interior, slowly moved these landmasses, causing them to fracture, collide, and reshape themselves over eons. Volcanoes acted as the architects of the planet, gradually building stable land where ecosystems would eventually form. Yet volcanoes did something even more extraordinary. They enriched the early oceans with vital minerals. Lava interacting with seawater released iron, sulfur, phosphorus, and a variety of trace metals, essential ingredients for life. Hydrothermal vents, also known as black smokers, became chemical factories where mineral-rich water mixed with heat and pressure to create complex organic molecules. Many scientists believe that life itself may have originated near these volcanic vents, where the right combination of energy and chemistry existed in a sheltered environment. These underwater volcanoes continue to operate today, and they remain some of the most biologically productive places on Earth. Entire ecosystems thrive around them, consisting of organisms that do not rely on sunlight at all. Instead, they depend on chemosynthesis, a process where bacteria convert volcanic chemicals into energy. These bacteria form the base of food chains that support worms, crustaceans, and even large tube-dwelling animals found nowhere else on the planet. In a sense, these modern ecosystems are living fossils, preserving ancient strategies for survival that may date back billions of years. Volcanoes also played a central role in regulating Earth's temperature. The early atmosphere, filled with greenhouse gases emitted by eruptions, trapped heat and prevented the planet from becoming a frozen world. Without volcanic activity, Earth could have been a cold, lifeless sphere, incapable of maintaining the liquid water necessary for life. The balance between volcanic eruptions releasing carbon dioxide and weathering processes removing it eventually created a stable climate, one of the rarest and most fragile planetary conditions in the universe. Another remarkable gift of volcanoes was the delivery of elements essential to biological molecules: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the backbone elements of life, were continuously recycled through volcanic activity. When lava weathered and broke down into sediments, it released nutrients that nourished early microbial communities. Volcanic ash, rich in minerals, spread across young landscapes, fertilizing environments that were just beginning to support life. Even today, volcanic soils are among the most fertile on Earth. Regions like Hawaii, Indonesia, and parts of Italy owe their lush vegetation to ancient and ongoing eruptions. Farmers who live near volcanic regions often benefit from the nutrient-rich earth, which supports crops far better than ordinary soil. This paradox, destruction followed by renewal, reflects nature's ability to transform violence into fertility. Volcanoes have also influenced evolution itself. Large eruptions have periodically reshaped the planet's climates and ecosystems, sometimes causing mass extinctions, but also creating opportunities for new species to emerge. The famous eruption that contributed to the extinction of the dinosaurs cleared the way for mammals and eventually humans. In this sense, volcanic activity acts not only as a creator, but as a sculptor of life's diversity. From deep time to the present, volcanoes remain deeply intertwined with life. Even the air we breathe today bears the signature of volcanic origins. Oxygen did not appear until billions of years after life began. But the early atmosphere set the stage for the evolution of photosynthetic organisms, which eventually oxygenated the world and made complex life possible. The oceans, too, still feel volcanic influence. Hydrothermal vents continue to create habitats where unique species thrive. Undersea eruptions reshape the seafloor, create new islands, and replenish dissolved minerals that feed marine life. Volcanoes even contribute to our modern biological cycles. They release carbon dioxide that helps maintain Earth's energy balance. They enrich soils that grow food for billions of people. They provide the geothermal heat used for sustainable energy in many countries. In a quiet, profound way, volcanoes remain the heartbeats of Earth's biosphere. It is easy to see volcanoes only as destructive forces, as mountains that erupt violently and reshape landscapes with fire. But beneath their dramatic eruptions lies a deeper truth. They are also creators, nurturers, and architects of life itself. Without them, Earth might have remained a barren planet of rock and ice. Every breath we take, every ocean wave, every living cell carries within it the legacy of ancient fire. Volcanoes may seem like symbols of destruction, but in the grand story of our planet, they are its first guardians, the keepers of warmth, water, minerals, and the chemical possibilities that made life bloom. Section 9. Volcanoes that hide beneath the waves. When we think of volcanoes, we usually picture towering cones rising above the landscape, their slopes etched with ancient lava flows, and their peaks shrouded in drifting plumes of steam. But in truth, most volcanoes on Earth are nowhere near the surface. They lie far below the waves, out of sight and out of reach, shaping the very foundation of the planet. From the quiet darkness of the ocean floor, these underwater volcanoes, submarine volcanoes, form one of the most mysterious and influential geological systems on Earth. And although they erupt more often than their land-based relatives, their activity remains largely hidden, softened by the immense weight of the sea. The world beneath the ocean is a realm of pressure so intense and light so faint that it reshapes the rules of nature at depths of thousands of meters. Volcanic activity unfolds in a way that feels strangely muted, as though the sea itself absorbs the violence and transforms it into something slow and steady. Lava that would explode into fiery fountains on land instead chills instantly into black, glassy fragments. Liquid fire becomes fragile stone in the blink of an eye, forming shapes found nowhere else. Pillow lavas, round and smooth, stacked like oversized beads. Their curved surfaces tell a story of molten rock meeting cold seawater, a dramatic interaction conducted in complete silence. One of the most astonishing places where this underwater drama plays out is along the mid-ocean ridges, vast chains of volcanic mountains stretching nearly 65,000 kilometers across the seafloor. These ridges are essentially the seams of the planet, where tectonic plates pull apart and molten rock rises to fill the gap. Every year, new crust is born here in a continuous, slow-motion eruption that has been going on for hundreds of millions of years. The ocean floor you see on any map, every valley, every ridge, every plain originated in one of these volcanic birthplaces. And yet, despite their scale, we almost never witness these eruptions firsthand. The sea conceals them completely, only in rare moments like in 1998, when scientists traveling along the East Pacific Rise captured the first ever footage of an underwater eruption. Do we get a chance to glimpse this hidden world in action? Through robotic cameras, they watched shimmering plumes of superheated water burst from cracks in the seafloor, carrying clouds of minerals into the surrounding darkness. The lava flowed like glowing rivers, forming new crust, even as robotic arms reached forward to collect samples. It was the quietest eruption ever filmed, and yet its significance was enormous. This was Earth in the act of recreation. But submarine volcanoes do not only build the ocean floor, they also shape the life around them. In fact, some of the most surprising ecosystems on the planet are found near hydrothermal vents, the chimneys formed by underwater volcanic activity. Here, water heated to hundreds of degrees by magma beneath the crust surges upward through mineral-rich vents. The water under extreme pressure doesn't boil. Instead, it pours out like shimmering liquid metal. As it meets the cold seawater, minerals harden into towering chimneys that rise like strange, otherworldly coral. Some reach heights of 20 meters or more. What surrounds these vents seems impossible. The darkness is absolute. The water is freezing, just centimeters away from scorching jets of vent fluid. And yet this is where life thrives. Tube worms with crimson plumes, sulfur-eating bacteria, ghostly white crabs, blind shrimp, and creatures that look like characters from forgotten myths, all building their existence on chemistry rather than sunlight. In a way, these volcanic vents are portals to Earth's earliest years, when life may have begun in similar environments. Some researchers believe that hydrothermal vents are not just biologically rich. They may be the cradle of life itself. Further out in the oceans, other submarine volcanoes grow quietly until one day they break the surface, forming brand new islands. This is how the Hawaiian Islands were born, one after another, in a slow volcanic march across the Pacific. Even today, the next Hawaiian island, called Loihi, is rising beneath the waves, still hidden, but growing steadily. It will likely emerge above sea level thousands of years from now, an island waiting in the wings. Submarine volcanoes can also surprise us in ways we do not expect. In 2012, a massive underwater eruption near Tonga produced one of the largest pumice rafts ever recorded. Pumice, lightweight, air-filled volcanic rock, floated to the surface and formed a drifting island the size of Manhattan. Sailors who encountered it described an eerie sight, a seemingly endless field of pale stone, stretching so far that it blocked the waves. The eruption that caused this raft took place deep underwater, and yet before long, the pumice carried organisms across the sea like tiny travelers on a geological arc, helping them colonize distant shores. Perhaps one of the most dramatic examples of how underwater volcanoes shape our world came in 2022, when the Hunga Tonga Hunga Ha'apai volcano erupted with a force so immense that it affected the atmosphere of the entire planet. Satellite images showed a shock wave rippling around Earth multiple times. Although the volcano's summit was underwater, the explosion was powerful enough to tear through the surface and blast ash 58 kilometers high into the mesosphere, an altitude no eruption had reached before. The eruption rearranged the seafloor, destroyed islands, and triggered tsunamis across the Pacific. Yet even this event was only a glimpse of the immense energy stored beneath the ocean. And still, for all their might, submarine volcanoes remain among the least explored features on Earth. More people have stood on the surface of the moon than have seen a mid-ocean ridge up close. The deep sea resists exploration with its crushing pressure, freezing temperatures, and complete darkness. Robotic probes, armed with lights and cameras, venture carefully into these depths. But the ocean still guards many secrets. Entire volcanoes may exist that we have never detected. Entire eruptions may have happened without leaving a trace we can observe. And so, hidden from human eyes, underwater volcanoes continue their silent work. They build mountains we will never climb. They fuel ecosystems we are only beginning to understand. They reshape the planet slowly, steadily, rhythmically, like the heartbeat of a world wrapped in water. In the quiet darkness beneath the waves, volcanoes breathe out heat and minerals, creating life where none should exist and sculpting landscapes no human has ever seen. They are reminders that Earth is alive, not just on the surface, but deep below, alive in places where daylight never reaches and where the only illumination comes from the soft glow of molten stone. Section 10. The mysterious signals volcanoes send before they erupt. Before a volcano erupts, the earth begins to whisper. These whispers are subtle at first, tiny shifts, delicate tremors, faint chemical fluctuations. But to those who know how to listen, they form a language all their own. What makes volcanoes so captivating is that they rarely erupt without warning. Instead, they prepare themselves through a sequence of changes that reveal the rise of magma from the deep. These signals are mysterious, elegant, and often surprisingly calm, as though the volcano is taking a deep breath before speaking through fire. The first sign often comes from deep beneath the ground, where magma, slowly pushing its way upward, cracks the rocks around it. These cracks produce seismic waves, volcanic earthquakes, that differ from the ones produced by shifting tectonic plates. They tend to be softer, repeating, almost rhythmic. Scientists call them long-period earthquakes, and they often occur in clusters, like a distant drumbeat. The earth seems to thrum gently, building a pattern that can last for days, weeks, or even months. For volcanologists, this is one of the earliest and most reliable clues that something is stirring below. But seismic waves are only part of the story. As magma rises, it releases gases, carbon dioxide, sulfur dioxide, and water vapor. These gases begin to seep upward through cracks and fissures, sometimes escaping into the atmosphere at the summit of the volcano. Instruments perched on crater rims or flown overhead by drones detect these subtle chemical changes. A sudden increase in sulfur dioxide, for example, often suggests that fresh magma has reached a shallow depth. It is as if the volcano is exhaling, its warm breath carrying the scent of molten stone. In some places, scientists measure these gases not just at the summit, but through the soil around the volcano. Carbon dioxide, being heavier than air, tends to gather in low-lying areas. If it begins to accumulate in unusual concentrations near the ground, it may indicate gas escaping from deep magma chambers. In certain volcanic regions, like Italy's Campi Flegrei or California's Mammoth Mountain, CO2 seepage has become so intense at times that entire forests have died from suffocation. These tragic events serve as reminders that volcanoes communicate long before they erupt, and that their messages can reach even the quiet edges of the landscape. Another signal lies in the shape of the volcano itself. As magma collects beneath the surface, the ground begins to swell. This inflation can be subtle, a few millimeters at first, or dramatic, as entire hillsides lift upward like slow-motion waves. Scientists use GPS stations, laser reflectors, and satellites equipped with radar to measure these changes with incredible precision. Space agencies can now detect when the flank of a volcano swells by less than the width of a fingernail. It is extraordinary to think that from hundreds of kilometers above Earth, we can watch a mountain breathe. Sometimes this swelling produces visible cracks in the ground. These fractures, appearing suddenly across roads or through forests, are not yet eruptions, but hints of tension building below. Lava has not reached the surface, but the pressure is growing, stretching the landscape into new shapes. These cracks are like quiet scars, delicate signatures of magma on the move. Volcanoes also change their thermal behavior before erupting. Heat begins to seep upward, warming the ground, melting snow, and altering water flow. Hot springs may become hotter, fumaroles may intensify, and underground reservoirs may shift in temperature. Some volcanoes develop new geysers or alter their hydrothermal systems entirely. In Iceland, for example, several geothermal valleys have been reshaped over the years as volcanic heat waxes and wanes beneath them, creating new pools while silencing others. And there is one more type of signal, one of the strangest and most difficult to measure: volcanic infrasound. These are sound waves pitched so low that no human ear can detect them. They roll through the air like invisible tides, traveling vast distances. As magma moves, as gases rumble, as vents begin to open, infrasound patterns shift. Some scientists describe them as the voice of the volcano, speaking in frequencies that only specialized microphones can hear. Listening to infrasound is like tuning into a secret conversation happening beneath the Earth's crust. What makes all of this truly remarkable is how each volcano has its own personality. Some erupt violently, with very little warning, while others spend months announcing their intentions. There is no universal pattern. Each system behaves according to its own internal architecture, its magma composition, its gas content, its geological history. Two volcanoes of the same size may produce completely different signals. It's this uniqueness that makes volcanic forecasting challenging, but also endlessly fascinating. Consider Mount St. Helens in 1980. In the months before its catastrophic eruption, the volcano bulged massively on its northern flank. Entire forests shifted as the ground rose dramatically. A visible dome of rock grew outward at an astonishing rate, about 1.5 meters per day. For volcanologists, this was an unmistakable sign of magma pushing upward. Yet the eruption that followed was not the vertical blast many anticipated. Instead, the swollen flank collapsed, triggering a lateral explosion unlike anything recorded in modern times. In contrast, Japan's Mount Fuji has been largely quiet since 1707, even though it sits in a region ripe with seismic activity. Fuji produces occasional tremors and gas releases, but its signals remain calm, steady, almost restrained. Scientists watch it constantly, aware that a future eruption could have major consequences, yet they also recognize that the volcano speaks softly, even when its internal systems shift. In other cases, volcanoes provide warnings that seem almost gentle. Before Iceland's Eyjafjallajökull erupted in 2010, seismic activity increased over several weeks, accompanied by small swarms of earthquakes and subtle ground swelling. The eruption that followed was not especially large in geological terms, but the ash it produced disrupted air travel across Europe for days. It was a humbling reminder that even minor volcanic events can ripple far beyond their immediate surroundings. And then there are volcanoes like Kilauea in Hawaii, which erupt with such regularity that their signals form a kind of rhythm. For decades, Kilauea has offered scientists an unparalleled window into the inner workings of a volcano. Slow lava flows, shifting vents, frequent gas emissions, and calm, predictable seismic patterns. Watching Kilauea is like studying the heartbeat of the Earth, steady, warm, and revealing. Yet for all our monitoring systems, volcanoes can still surprise us. Their signals can change suddenly. Some warnings are subtle enough to be missed, while others may suggest an eruption that never arrives. A volcano can shift from restless to silent in a single day. The Earth may speak clearly at times and murmur at others, but one truth remains: volcanoes rarely erupt without sending some sign into the world. And as our instruments become more sensitive and our understanding grows deeper, we are getting better at interpreting these ancient signals, better at hearing the murmurs beneath our feet, better at recognizing the delicate hints of heat, sound, and movement that precede an eruption. Volcanoes do not merely erupt, they communicate, and listening to them is one of the most profound ways we connect with the living Earth. Section 11. The mysterious signals volcanoes send before they erupt. Before a volcano erupts, it begins to whisper. These whispers are subtle at first. Tiny tremors, slight gas emissions, small shifts in the ground, but to those who listen carefully, they form a language all their own. Volcanoes rarely erupt without warning. Instead, they announce their intentions gradually, sometimes over weeks, months, or even years, offering clues to the careful observer. The signs may be delicate, but they reveal the hidden dynamics of molten rock moving deep beneath Earth's surface. One of the most revealing signals comes from seismic activity. Magma does not rise silently. It pushes against solid rock, forcing fractures and small earthquakes. These volcanic tremors are different from ordinary tectonic quakes. They tend to be long-period events, repeating softly and rhythmically. Scientists describe them as the Earth's heartbeat, a low, persistent pulse that reflects the motion of magma as it makes its slow, upward journey. Each tremor is a message, signaling that the volcano is stirring, that pressure is building, and that molten rock is on the move. Gas emissions are another crucial signal. Magma contains dissolved gases, carbon dioxide, sulfur dioxide, water vapor, and other trace compounds. As it rises, the pressure decreases, and gases begin to escape through cracks and fissures. Measuring these emissions allows scientists to understand what is happening beneath the surface. A sudden spike in sulfur dioxide, for instance, often indicates that fresh magma has reached shallow depths, preparing to breach the surface. In some volcanic regions, gas releases have been so strong that they affect entire ecosystems, killing vegetation and warning of the underground activity. Ground deformation is equally significant. As magma accumulates beneath a volcano, it pushes the Earth's crust upward, causing subtle swelling. Modern GPS and satellite technology allow scientists to detect changes in elevation of just a few millimeters. These measurements reveal inflation and deflation cycles, providing clues about the amount of magma rising and the pressure it exerts. When these changes accelerate, the likelihood of an eruption increases. Ground cracks, tilting slopes, and shifting ridges may also appear as tangible signs that the mountain is preparing to awaken. Temperature shifts and hydrothermal activity are additional signals. Rising magma warms surrounding rock and underground water systems. Hot springs may increase in temperature, fumaroles may intensify, and geysers can appear or change their patterns. These phenomena are subtle yet critical, showing that heat is reaching the surface. Even slight variations in water chemistry can indicate the presence of magma below, providing early warning of potential eruptions. Infrasound, sound waves too low for humans to hear, is another signal of volcanic activity. These vibrations travel long distances through the air and reflect changes in gas emissions, explosions, or magma movement. By listening to these inaudible waves, volcanologists can hear the volcano preparing for eruption, even when it seems completely silent. Infrasound recordings capture patterns of activity that complement seismic and gas measurements, creating a full portrait of the volcano's internal behavior. Each volcano has its own personality. Some, like Mount St. Helens in 1980, provide dramatic and unmistakable warnings: bulging slopes, visible dome formation, repeated earthquakes. Others, like Mount Fuji, may show only subtle tremors or minor gas emissions, remaining calm for decades before erupting. Even volcanoes that erupt frequently, such as Kilauea in Hawaii, follow their own internal rhythms, offering scientists rare opportunities to observe predictable sequences of behavior. Volcanoes also send chemical signals into surrounding soils. Carbon dioxide and other gases can seep into the ground, accumulating in depressions and valleys. In extreme cases, these gases can be deadly to plants and animals, revealing underground activity before magma ever reaches the surface. This is a reminder that volcanic warnings are not only physical, they are chemical, environmental, and sometimes biological, influencing everything around the mountain. Despite our ability to detect these signals, volcanoes can still surprise. Some signs are subtle, others ambiguous, and the timing between a warning and eruption can vary greatly. A volcano might show weeks of increased tremors, only to return to quiet before erupting months later. This unpredictability highlights the delicate balance between Earth's internal forces and the observable effects on the surface. Yet with each signal recorded, our understanding grows, allowing humans to coexist more safely with these living mountains. Historical examples illustrate these dynamics vividly. The eruption of Mount Pinatubo in 1991 was preceded by weeks of earthquakes, steam explosions, and ground swelling. Scientists recognize these warnings, allowing the evacuation of tens of thousands of people and saving countless lives. In contrast, eruptions without clear signals, though less common, demonstrate the limits of human observation and the power of Earth's hidden forces. Ultimately, volcanoes communicate through many channels: earthquakes, gas emissions, ground deformation, thermal shifts, and infrasound. They do not speak in words. Yet their messages are unmistakable to those who understand the language of fire and rock. Listening to these whispers is a profound way to connect with the earth, to witness the quiet, patient processes that unfold beneath the surface, often unnoticed for centuries. Volcanoes are not merely destructive forces, they are living systems, dynamic and sensitive. Their signals remind us that the planet beneath our feet is alive, constantly moving, constantly preparing for change. By paying attention to the tremors, gases, and shifts in the ground, we not only anticipate eruptions, but also gain insight into the inner workings of the earth, the hidden rhythms of molten rock, and the delicate balance that sustains our world. In listening to these signals, we find awe and understanding. Volcanoes do not erupt without warning. They speak in vibrations, exhalations, and shifts in stone. And if we are attentive enough, we can hear the story of the molten earth, unfolding slowly beneath the surface, a tale of heat, pressure, and the slow, deliberate movement of the forces that shape our planet. Section 12. The role of volcanoes in shaping landscapes and ecosystems. Volcanoes are often thought of as destructive forces, capable of wiping out entire cities and forests in moments of fiery eruption. But in reality, they are also master sculptors of landscapes and caretakers of ecosystems. Their influence is profound, extending far beyond their immediate surroundings. Over geological time, volcanic activity has shaped continents, created fertile soils, carved valleys, and formed islands. Volcanoes do not just destroy, they build, enrich, and sustain life in ways both subtle and dramatic. One of the most visible ways volcanoes shape landscapes is through the creation of mountains and islands. Each eruption deposits layers of lava and ash, slowly building up conical peaks that can tower thousands of meters above sea level. The Hawaiian Islands, for example, are a chain of volcanic mountains formed by the Pacific Plate moving over a stationary hotspot in the Earth's mantle. Each island tells a story of repeated eruptions, slow lava flows, and gradual emergence from the ocean. Even after an eruption ceases, the topography it creates persists, forming habitats for countless plants and animals. Islands that rise from the sea become laboratories for evolution, where species adapt to isolated conditions, giving rise to unique forms of life found nowhere else. On continental landmasses, volcanic activity carves valleys, plateaus, and plains. Lava flows can dam rivers, redirecting water and reshaping entire drainage systems. Pyroclastic flows, fast-moving currents of hot gas and volcanic material, flatten landscapes, only to create new substrates that over time host forests and grasslands. Volcanic eruptions have been responsible for forming entire mountain ranges, such as the Andes, where a chain of volcanoes stretches thousands of kilometers along South America's western edge. These features are not just aesthetic. They create microclimates, rain shadows, and fertile basins that support life in regions that might otherwise be barren. Volcanic soils are among the most fertile on Earth, a remarkable gift to life that arises from what initially seems destructive. When lava cools and weathers, it releases minerals and nutrients essential for plant growth. Phosphorus, potassium, calcium, and trace metals become part of the soil, nourishing crops and wild vegetation alike. In countries like Italy, Japan, and Indonesia, communities have farmed volcanic soils for centuries, growing abundant rice, coffee, fruits, and vegetables. Even today, volcanic soils sustain ecosystems that thrive in what would otherwise be challenging conditions, turning once barren slopes into lush forests teeming with biodiversity. Volcanic ash also plays a vital role in shaping ecosystems. While catastrophic eruptions can temporarily devastate forests, the ash eventually settles, forming a rich layer of mineralized soil. It replenishes nutrients leached from the ground by rain and erosion, rejuvenating the land for new life. In this sense, eruptions act as cycles of destruction and renewal, where the short-term havoc sets the stage for long-term ecological productivity. Water systems are intimately influenced by volcanic landscapes. Lava flows can redirect rivers, form natural dams, and create crater lakes. These lakes become habitats for amphibians, fish, and birds, often supporting species adapted specifically to volcanic environments. Groundwater can be heated by geothermal activity, forming hot springs that sustain unique microbial life. While rivers enriched by mineral runoff feed downstream ecosystems. Volcanic landscapes are, in essence, blueprints for water distribution, providing both the physical structure and chemical richness necessary for diverse life forms. Forests that grow on volcanic slopes are among the most biologically rich ecosystems on Earth. The fertile soils allow dense vegetation, while the slopes create diverse microhabitats, shaded valleys, exposed ridges, and sheltered crevices. Each eruption reshapes these forests, creating a mosaic of old-growth trees, pioneer species, and regenerating areas. Animals adapt accordingly, exploiting the variations in elevation, moisture, and vegetation. Birds, insects, and mammals thrive in these patchwork habitats, each species occupying a specific niche created by the volcano's past activity. Volcanoes also influence climate locally, which further affects ecosystems. Large volcanic mountains can intercept clouds and increase rainfall on windward slopes, while creating rain shadows on the leeward side. These microclimates support unique plant communities and influence the distribution of animal populations. The Andes, for instance, host cloud forests on volcanic slopes that are unlike the lowland forests below, harboring species that exist only in these elevated volcanic habitats. Similarly, volcanic islands often develop multiple climate zones within a few kilometers, creating rich ecological diversity in a small area. Submarine volcanoes, hidden beneath the ocean, similarly shape ecosystems in profound ways. Hydrothermal vents emit mineral-rich water that supports life in complete darkness. Chemosynthetic bacteria form the base of complex food webs, supporting tube worms, crabs, shrimps, and other creatures. Underwater eruptions reshape the seafloor, creating new habitats for colonization, while pumice rafts generated by eruptions carry organisms across oceans, connecting distant ecosystems in unexpected ways. Even in the cold, high-pressure environment of the deep sea, volcanoes act as architects of life. In the long term, volcanic activity contributes to evolutionary pressures that drive biodiversity. By periodically disrupting habitats through eruptions, lava flows, or ashfall, volcanoes create opportunities for species to adapt, migrate, or speciate. Islands formed by volcanoes become isolated evolutionary laboratories, while periodic disturbances on continental volcanoes favor pioneer species and ecological succession. In this sense, volcanic landscapes are dynamic classrooms, teaching resilience, adaptation, and survival. In essence, volcanoes are both creators and sustainers. They build mountains and islands, enrich soils, sculpt water systems, and foster biodiversity. They connect geological processes to life in ways that remind us of the interdependence of Earth systems. Without volcanic activity, the world would be flatter, soils poorer, forests less dense, and ecosystems far less varied. Volcanoes, often feared for their immediate destructive power, are ultimately guardians of long-term fertility and complexity. Even the most seemingly barren volcanic landscapes are alive in their subtle, ongoing transformation. Lava slowly weathers into soil. Ash settles into nutrient-rich layers. Rivers find new paths. Forests reclaim slopes, and wildlife adapts to the patterns of eruption. The volcano does not destroy in vain. It builds in cycles, leaving a legacy of landforms and ecosystems that would not exist otherwise. It is the quiet pulse of creation, hidden within fire, a reminder that the Earth's fiery heart shapes life itself. Section 13. Volcanic Extremes, the coldest and highest volcanoes on Earth. When we imagine volcanoes, our minds often picture glowing lava, ash clouds, and tropical islands. But not all volcanoes fit this fiery stereotype. Some of the most fascinating volcanic landscapes exist where ice dominates, where snow drapes slopes in perpetual white, and where extreme altitudes challenge life itself. The coldest and highest volcanoes on Earth exist in a delicate balance between fire and frost, demonstrating that volcanoes are not just destructive forces. They are paradoxical wonders, combining heat and cold, activity and stillness, danger and sublime beauty. High-altitude volcanoes are often found along the Andes Mountains, the Himalayas, and other tectonically active ranges. These volcanoes rise thousands of meters above sea level, with peaks piercing the thin air where oxygen is scarce and temperatures plummet. Some are permanently capped by glaciers, even while magma simmers beneath. Ojos del Salado, straddling the border of Chile and Argentina, is the highest active volcano in the world, reaching over 6,893 meters. Its slopes are a stark contrast. Jagged black lava flows juxtaposed with brilliant snowfields, a frozen landscape warmed by hidden magma. Few humans have dared to explore these heights, but the mountain quietly pulsates with volcanic energy, reminding us of Earth's dual forces of fire and ice. Extreme cold adds a unique dimension to volcanic activity. Magma rising beneath glaciers can trigger sudden and violent interactions with ice, producing explosive eruptions called phreatomagmatic eruptions. When molten rock meets glacial meltwater, the rapid expansion of steam fragments the lava into fine ash, blasting it skyward. These eruptions are dangerous yet strangely beautiful, creating towering plumes that glitter with frozen particles. Iceland's Eyjafjallajökull eruption in 2010 is a modern example, where glacial ice met magma to produce widespread ash clouds that disrupted air travel across Europe. These interactions demonstrate the delicate and unexpected ways that volcanoes shape their cold environments. Glaciated volcanoes also play an essential role in Earth's water systems. Melting ice from volcanic slopes feeds rivers and lakes, sustaining ecosystems far from the eruption itself. In many Andean regions, volcanic glaciers provide critical freshwater for agriculture and human populations below. Beneath the ice, geothermal heat maintains subsurface rivers and creates subglacial lakes that harbor unique microbial life. These hidden habitats remind us that life can exist in the most unlikely volcanic environments, adapted to both cold and heat in extraordinary ways. Volcanoes at high elevations experience extreme weather that affects both geology and biology. Snow, ice, and freezing winds sculpt their slopes, eroding lava flows and ash deposits into sharp ridges and valleys. These climatic extremes create habitats for specialized plants and animals that thrive in the margins between life and desolation. In these high-altitude ecosystems, volcanic soil provides nutrients, while the sparse air limits competition, allowing hardy species to persist. Even microorganisms flourish beneath volcanic rocks, metabolizing minerals and surviving temperatures that would kill most life forms. The coldest volcanoes also reveal how glaciers and fire interact over geological time. As eruptions deposit lava and ash, glaciers slowly grind them down, redistributing material across valleys and creating fertile plains at lower elevations. This interplay forms rich soils for future forests, meadows, and grasslands. Despite their extreme and barren appearance, glaciated volcanic regions are thus nurseries for ecosystems, slowly building landscapes that support life. In addition to high-altitude extremes, volcanoes in polar regions, such as Antarctica's Mount Erebus, present unique phenomena. Erebus, the southernmost active volcano on Earth, lies beneath harsh, frozen winds and near complete darkness for months during the Antarctic winter. Yet it hosts a persistent lava lake, a rare, molten pool glowing within its icy crater. Scientists visiting Erebus describe a surreal scene: steam plumes rising against a backdrop of snow and ice, red-hot molten rock visible in the heart of a frozen continent. Life exists here too, in the form of extremophiles, microbes adapted to survive both heat and cold. Erebus is a reminder that volcanoes can thrive in isolation and extremes, maintaining vitality in places that seem inhospitable to most living creatures. The combination of altitude, cold, and volcanic energy creates natural laboratories for scientific discovery. Studying high and cold volcanoes allows researchers to understand how magma behaves under extreme pressure and temperature, how ice influences eruptions, and how ecosystems adapt to volcanic hazards. Insights from these places also inform our understanding of other planets and moons, where volcano-ice interactions may have shaped landscapes long before life appeared. In a sense, Earth's coldest and highest volcanoes offer a glimpse into worlds beyond our own. Despite their beauty and scientific importance, these volcanoes are often overlooked. They do not draw the attention of tropical eruptions or iconic lava flows, yet their influence on Earth's geology and life is profound. They sculpt mountains, feed rivers, provide unique habitats, and even influence global climate by injecting ash and gases into the upper atmosphere. Their presence reminds us that volcanic activity is not limited to fire alone. It is a force that integrates heat, ice, altitude, and life in a single extraordinary system. Exploring these volcanoes also inspires a sense of humility and awe. Standing on a snow-draped peak where molten rock churns beneath one's feet, it is impossible not to feel the scale of Earth's processes. These are landscapes shaped by eons of fire and ice, where extreme conditions test both life and human endurance. They teach us about resilience, adaptation, and the interconnectedness of geological and biological systems. In these extreme environments, volcanoes are both sculptors and guardians, quietly shaping life and landscapes in ways that are often invisible to the casual observer. Ultimately, the coldest and highest volcanoes are reminders of Earth's paradoxical nature. They combine heat and frost, life and desolation, power and subtlety. Their extreme conditions create some of the planet's most unique geological and biological features, from subglacial lava formations to microbial ecosystems thriving in isolation. They are silent teachers, showing us that even in the harshest conditions, life and creation endure. Volcanoes are not merely hazards, they are architects of landscapes, reservoirs of energy, and nurturers of life in extraordinary and unexpected ways. Reflecting on Earth's fiery heartbeat, volcanoes are more than mountains of fire and ash. They are living, breathing forces that shape the Earth's surface, influence climate, create life, and even cradle ecosystems where none might exist. From the hidden depths of the oceans to the icy heights of Antarctica, from the rhythmic tremors beneath our feet to the fertile soils that sustain entire forests, volcanoes remind us of the extraordinary ways in which the Earth renews and sustains itself. By observing their signals, exploring their extremes, and understanding their ecosystems, we gain not only scientific insight, but a profound appreciation for the balance of destruction and creation that governs our planet. Volcanoes are the Earth's heartbeat, sometimes violent, often subtle, but always alive.